Now, protons and neutrons have approximately the same mass, okay, and they're given right here in this slide. Okay, you can see it's 1.67 times 10 to the negative 27 kilograms, 1.6749 times 10 to the negative 27. So the proton and neutron have almost the same mass, and they're much more massive compared to the electron. In fact, a proton is 1,836 times more massive than an electron. I've purposely written it this way here, the mass of the electron, 0.00091 times 10 to the negative 27. Okay? Now, these masses are kind of hard to remember, so we've invented a unit called the atomic mass unit. So this U right here is atomic mass unit. Okay, so that stands for atomic mass unit. Oftentimes it's abbreviated as AMU, okay? But U is also a little more is the correct abbreviation for it. Okay, so mass of the proton would be 1.0073 atomic mass units. The mass of the neutron is 1.0087 atomic mass units, but the electron is 0.0005 atomic mass units. So you can see how small the electron is in terms of mass compared to the proton and neutron. What does this mean in terms of the mass of the atom? It's concentrated in what part of the atom? The nucleus, because that's where you find the protons and the neutrons. So around the electron, around the nucleus, is really mostly empty space. It's hardly any mass there too, because all you have there is the electrons. Okay. You don't have to remember this 7.3 and this 8.7. You can just, in fact, remember it to the nearest first decimal place, to a tenth of an atomic mass unit. A proton and a neutron would have a mass of 1 atomic mass unit, and the electron mass to the nearest first decimal, if you round up to the first decimal, is basically 0. In other words, we're saying electrons contribute hardly anything to the total mass of the atom. That is why the mass number, the number that we put in the name of the isotope, is just the total number of nucleons. So for example, if we have, let's say when we said oxygen 18, what did we say the 18 was? It's the number of protons plus the number of neutrons. Okay, so this 18 right here, we call this the mass number. Okay, that's not the actual mass of the atom, but the mass in atomic mass units, that would be pretty close to the mass of the atom. Okay, rounded anyway to the nearest whole number, that would be the mass of the atom in atomic mass units. Doesn't include the number of electrons. Okay, let's look at this. Which one has the largest mass? 1 proton, 3 electrons, or 2 neutrons? 2 neutrons. Very good. Approximate mass here is about 2 atomic mass units, right? Approximate mass of a proton would be 1 atomic mass unit. What's the approximate mass of 3 electrons? Okay, 3 times 0.0 is still 0. Okay? Now, for very precise work, we cannot just add up the masses of electrons, protons, and neutrons to get the total mass of an atom. So, for example, oxygen 18, remember, oxygen has 8 protons, right? Atomic number is 8. The 18 means it's got 10 neutrons. Okay, oxygen 18, the neutral atom, will have the same number of electrons and protons. It will have 8 electrons. Now, if you just add up the masses of the protons and the neutrons, what was the mass of the proton? If you remember, it's 1.0073. Was it 73? Proton 73, and then neutron is 87, right? And the neutron is 10 times 1.0087. This should be a number higher than 18, right? 8 times 1, 10 times 1, 8 plus 10 is 18. But this is more than 1, right? So this must be larger than 18. But the mass of an oxygen 18 atom is, in fact, if you look it up, okay, it's only 17.991803. No, the electrons don't have a negative mass. If you add the mass of the electrons, there's even more. Okay? So this discrepancy is known as the mass defect. Okay? And basically the way we explain that is that in order for these particles to come together to form a stable atom, they have to lose energy. Okay? So you have to put that energy back in order to separate the atoms. So this number we have here, if we just add up all the masses, those would be the masses of the particles separately. If they're all separate from each other, you add up their masses, you get a number higher than 18. But if you put them together in an atom, the atom, and you get a stable atom, then they have to lose mass. Okay, so you say there's conversion of mass to energy. Okay, and so we have to put energy back in order to separate these particles from each other. And the formula for that is given by Einstein's famous equation, E equals mc squared. So E is the mass defect in this case, okay? And C is the speed of light. Oh, I have it right here. Okay. So that would be that. If you calculate the if you multiply the mass by the square of the speed of light, you get what's called the binding energy. That's the energy you need to separate the particles from each other.